Everybody. I think I know absolutely everybody in this seminar. If not, my name's Dr. Alan Burden. I'm one of the postdocs in Program 3 at the ACC. This is the overview and summary at the end of the project 3.6, which is a translation project with B&R Enclosures. And this is titled the XR Application for Cobot Interaction and Workflow Optimization. Let me just double check. Slide. Hopefully you can see that. It's a bit of a lag. Okay, excellent, good. So this project was born out of kind of a bit of a challenge and lots of questioning about how difficult is it for somebody who walks in off the street to be able to program a cobot, not an industrial robot, but just a cobot, or at least to be able to communicate with a cobot and get it to do a set of tasks and understand that relatively quickly and learn while they're doing that. In review of some of the methods of interacting with cobots, generally when you buy a commercial cobot off the shelf, it comes with one of these teaching pendants. They are getting gradually better, but the foundational problem of this is that they're generally rooted in the previous pendants, which were always designed for industrial robotics, which allows for a great deal of versatility and programming, but not very user-friendly. And as you can see, they're generally all of the big major brands there, which is Fanuc on the left. That's the new Universal Robotics tablet at the top there, the three. ABB in the center, and at the bottom there, that absolute Goliath, and very heavy Cobot interface from KUKA. They haven't changed a tremendous deal since they've come out. It's the interface that gets updated quite regularly, but they are still quite heavy. This is what the interaction generally looks like. You'll often see people with terrible posture, hunched over a tablet. Trying to do anything that takes a great deal of time with one of these tablets is quite problematic. You find yourself generally sitting down. I've had a lot of time with the UR pendant and also with the KUKA pendant. You generally want to rest it on a table and program it that way, or at least try and have a link with a computer to try and program it through a computer instead. Both of these things just take time, and it generally just takes a bit of getting used to the system and also understanding what it's capable of, because there are just so many options. The one that's worth noting is in the top left, the KUKA there, which is highly staged. It's somebody there doing what looks like learning by demonstration. But what's missing there is the fact that it will be somebody which will be holding the pendant to control that in the center image at the bottom there. Somebody will have to be using the pendant and holding it in order for that. So that's a two-person job, which they've like neatly kind of avoided showing in there. So the aims of this project were relatively broad, but they were kind of developing on a previous project that we did using Unity and ROS. Robot operating system, and that was to see if we could do the visuals and the interface within Unity and then get ROS to control the robot or control the simulation of the robot and to control other physics as well. This project changed in that we left Unity behind because there was some bureaucratic changes within Unity as a company. And also it was a good excuse to kind of look at the other games engines that are out there, and because Unreal Engine 5 had just come out, or came out a year ago, has been regularly updated, and there is definitely a focus towards using Unreal Engine for augmented reality, as with all the games engines, but they've done a lot of work with their packages. What did not exist was a connection to ROS, so we had to develop that ourselves as part of this project AIM. And additional to that is to kind of answer that question again of how could we get a person from off the street to be able to assign a cobot to do actions without actually programming the cobot. What's the way that we could do that? So a highly exploratory interface for robotics under development as part of a design process. And also to kind of explore early planning and visualization, see how easy it was to set this up and how we could kind of adapt it for other situations now that it's set up. Just a quick look at augmented reality. This is probably a bit of overkill for many people who are looking in this space. In the umbrella of all of the reality technologies, which is generally termed extended reality now, XR, augmented sits towards the real environment end. So we are looking very much at the physical or real world, and you get an overlay of the digital elements. So Pokemon Go, which many people know, well, was a mobile phone game, and that did a lot to kind of promote augmented reality and to show that it could actually be used in a real situation, a real world environment, although it was just playing a computer game. And because of that, augmented reality has become highly useful for training exercises and in use of games as well. The theoretical background behind this is based on embodied interaction, and this is an area which has been promoted from through AR. It was termed originally by Paul Durish, who is an interaction designer, wrote this incredible book, which is a very easy read, and I highly recommend it as just a read for anybody, because he writes well and it's very interesting. So the book is Where the Action Is, the Foundations of Embodied Interaction. Durish outlined this, which is shown in the diagram here, that when you have social context and physical context in interactions, that you have what he termed embodied interaction between the user and objects, but also that environment. And that also kind of develops an element of meaning and making. You associate new attributes through the interaction because of the physicality of what you're doing at the time, which is why it's often better for people to learn by doing rather than actually just being told what to do. Very slow slides. Sorry, a bit of a lag. Within AR, this adds an extra level in the fact that when you have a learner using augmented reality, particularly if you kind of remove the barriers and the difficulties of augmented reality, you find that generally doing a physical interaction or within a social context as well, having other people there, the embodied interaction adds another layer. So the meaning and the making is also attributed to what they are learning at that time as well. So this is the basis of why augmented reality studies generally will fall back on theories around embodied interaction and participant design as well. So the technology has been moving quite rapidly. This project, when we started, we were reviewing it with a Meta Quest Pro, which is what we developed on through Unreal Engine 5. And you can see that back then it showed the real environment in black and white through the cameras, which is referred to as pass-through. So you're looking at the screen or the real world projected via the cameras of the system, not with your real eyes. That was released at the end of 2022. Less than a year later, the Meta Quest 3 was released for less than half the price of the Pro. The Pro is now not available anymore. The Quest is much better, much lighter, better battery life, better everything, and is also in color, and is now getting close to the point of where the difficulties of wearing one of these headsets and how heavy they are and difficult they are to use is now starting to be reduced. And the kind of projections is that we'll get to the point where you'll wear these headsets very close to something like a pair of safety visors or glasses quite soon, as long as the battery life can be supportive of that. A quick plug for our paper, which we did in the process of reviewing and doing a scoping review for this project. We looked at interface design and how specifically for pick and place tasks, how AR could be used or was used in different projects. So this was a review of industry and research projects. And we did 55 papers, I believe, and at the end of it, a coding of the different attributes for how AR can generally help with human robotic interaction, specifically in pick and place robotic tasks. The 6 main findings were enhanced depth perception, is that you can actually put overlays to help with the perception. User-centered design is almost exclusively used in many of these developments of AR interfaces. hands-free interaction, multimodal interaction. Most of the expensive headsets have eye gaze capabilities, head movements they track, which means that you can have extra physical interaction with the system. Voice commands also helps, gesture commands as well. Now, real-time feedback and task guidance is paramount, as well as being able to allow context-specific help, which tends to be a great help for cognitive load reduction, which was the next finding. Simplifying or complicating the UI could be scaled based on the task, and then you've got collaborative interaction as well. So a quick overview of the system. On the left-hand side, the games engine was used to develop the visuals and the interaction system. That's through Unreal Engine 5.3, which was the most recent version. The application is compiled specifically for the headset, so everything runs on the headset, as opposed to the previous project where we ran everything on a computer and we fed that through Wi-Fi to the headset. So that makes it a bit lighter, and that means that we can use that headset anywhere. The connection to the ROS server is done through an iPhone hotspot, which we did to avoid the problems or the barriers of firewalls that we generally have at this university at QT. And we used VPN Tailscale as well to make sure that we did the straight connection through that PC, which was running Linux, I believe, Ubuntu. And the ROS server we had here at QT, we have tested this in quite a few places around Brisbane, and also when I went to Melbourne, we tested it across a 5G network, and it worked quite smoothly as well. The ROS server deals with the cobotic commands, the inverse kinematics, and also the physical nature of the blocks and boxes that you'll see in the demonstration when I show it in a couple of slides. So a quick work in progress demonstration. I will skip ahead to save a bit of time here. On the left-hand side, we have Unreal Engine, and you can see the setup of the system there with some green blocks or black blocks with the green edges on them. And UR10 robot in simulation in the center there. And on the right-hand side, we have ROS, which is running RViz as their representation visually. And we can control the robot in RViz, and we can get, it's a bit laggy at this point. This was from a very long time ago, but you can see that we have got an equivalent clone of it running in Unreal Engine. Lost my pointer, there we go. So the layout, this is looking down onto the scene. This will make more sense when I show the next video. But on the left hand of the scene, left-hand side, we have an input conveyor belt, which drops boxes into a little hopper, a table. The robot is sitting on a stand and can interact with the boxes, pick up the boxes, and then drop them onto output conveyors on the other side. There are these signaling boxes, which basically show each conveyor belt will be related to one of the boxes. This will make more sense in a second. And then in front of the user, who will be standing at the bottom of this scene, are 3 different stands, and on each stand are 3 different boxes, which are colored blue, green, and red. We did this in a big space, and the idea was to actually have people really walk around and get physical with moving around into that space as well. So this is the actual scene. You can see one of the stands there with a red block sitting on top of it. The green is in the center, and then the blue is on the other side. Big buttons on the wall, which you can trigger by basically pointing at them and hitting the trigger button, so you can start and stop and so on. This is quite laggy. I apologize. Pause it there. Ooh. There we go. Sorry. So we have on the other side of the scene, you can see the conveyor belts where the blocks will be distributed on from the by the robot, and each of those large blocks there will show that the robot knows to drop the red blocks onto that first front conveyor belt, the green into the center, and then the blue at the back, and so on. We deliberately gave the participants or the testers for this, we haven't had participants yet, very little information whatsoever, and to see how they would react. And this is one of the points of the system, just to see what they would do and how that could work around it and learn. So this is the actual scene. I'll see if this video works. Oh, it's buffering. I think it's trying to load. I don't think my MacBook's ever worked so hard in its life. So this is not a particularly big scene, but I think it's a long video. I might just pause it and see if it can buffer a bit quicker. I do. This worked fine in test run. So what we have is that generally whenever anybody tests this scene is that they work out very, very quickly that by moving the blocks onto the different stands at the front, that they can actually change which conveyor belt they are related to. Above the big signifying blocks, you have 3 small blocks. They are randomly assigned and they basically show the order in which you're meant to fulfill each of those orders. So you could have maybe 2 blues and a red, or 3 reds in a row, or 3 greens in a row, and so on. I'm just going to pause that because it's so jerky. It's giving me seasickness. I apologize that this video is not working. Let's see if it will play. No, sorry. I might have to post a video separately. I'm sorry about this. So you can pick up the blocks, move them onto the different platforms, and then it will change the color of the blocks in the background, the large blocks that we have there. The timer there is related to, basically, it's a good metric that we can kind of follow, but it also follows some of the theory behind Don Norman's work. Don Norman, who's done a lot of work in affordances and signifiers in interaction design, that he shows that whenever you put a timer into a system or show people that they're being timed, they generally try to be more efficient because they don't know why you're timing them, which does work well because people notice that they're being timed until after maybe a minute or two, and then they start to wonder why they're being timed for. I'll skip ahead and see if I can just grab some of the other scenes in this. So the blocks could continuously land on this area here, and they are randomly landing there. What we've found is that after about 2 or 3 minutes, when the blocks start to fulfill, people get impatient very quickly and they start to realize that they can interact with the scene. So they approach the robots and then they start to cheat by trying to pick up the blocks themselves and throw them onto the conveyor belt, which does not work. It has to be the robot that has to drop them onto the conveyor belt. But it was interesting to find that most people would do that. What they can do, however, is they can actually put the blocks into an order for the robot to then pick them up, which was the basis of what we wanted them to do. So if we know that they have a stack of 3 or 4 red blocks and they need a bunch of red blocks to be an urgent delivery, for example, then push them through first, stack them together, and the robot will pick them up earlier than the other ones. I'll skip on. I will post this video, I think, online. That's the way to get through that. So some of the key theoretical approaches behind this was embodied interaction with Paul Darush, as I mentioned. Spatial AI interfaces is generally built around the users moving through the space, but also with the control and understanding of the robot's actions, because they're both in the same physical space and embodied in that same environment. They have a better understanding of what the robot is doing rather than being separated by a screen. Tangible user interfaces, so placing physical, or in this case, the virtual blocks which you can physically interact with, coupling with the physical interaction allows for a tangible interaction. Although it's digital in this case, it means that people generally remember easier. External cognition, users will solve the logic puzzle by arranging things in AR, and they generally try to offload the thoughts that they have into space through action. The idea there is that you just do rather than think about it too much. Participatory design as well. The system invites use from non-programmers. So the key part of this is that industry settings is generally people aren't coders or they can't code a robot first. They need to be trained to do that. How do we overcome those barriers? Back to this diagram of embodied interaction is another layer here from after doing the research, is that it aligns quite well with some of the theories of why AR does work so well with training and learning. Situational cognition is the fact that in social and physical contexts is that you think better and remember better when you're in the situation where the task actually does happen. The embodied cognition which is through the interaction between the user and the objects, is that thinking is just not in the head. The bodies will help you figure things out. So by moving the blocks, you can actually see the results immediately, and then you remember and understand the system better. Inactive cognition is that you generally learn by doing, not by watching or being told. And the system does not really punish you for trying things out, and you can always reset it. You can't break anything. And embedded cognition as well, which is generally that the world around you will support your level of thinking as the stands that they sit on and the spatial layout hold some level of thinking or working it out, that the users generally they will then rely on what they can actually see and what they can actually touch as well. Another bit of functionality that was programmed into the system. I'll see if this video can work. So this is by pressing a combination of trigger buttons. It's also going to be quite laggy. Is that you can bring up this large bubble. The bubble shows the sweet spot, not the maximum reach of the robot. Most of these cobots have a sweet spot, which is a little bit shorter than the maximum reach where they should be used for most operations. The bubble indicates that you can use either hand on the controllers of the AR headset to click onto that bubble and get the robot to move there. These were the early testing to see how well we can actually program the robot to do this in simulation through ROS as well. So preliminary findings, we haven't done this with participants yet, just with testers, anybody walking past the lab at the time. So testers generally understood the block to convey a logic very quickly with under a minute for most of them. The spatial placement of the colored blocks on the stand was easily interpreted as a way of sorting through the instructions. They also discovered very quickly, once they got a little bit bored or frustrated, that they could rearrange the incoming blocks and showing kind of emergent solving behaviors, problem solving behaviors, or prioritize particular colors to go through. We gave no instruction whatsoever on the testers. We just said, try this. And we just sat there silently, and it was quite funny to watch. And most people worked it out very quickly. Some of them were scared to break the system, but generally once they did, they had fun with it. Timing and completion feedback did engage the testers as well. And did prompt them to try and work harder or quicker or to get the blocks through because they knew they were being timed. And the testers were naturally discussing their decisions out loud. So they, even in AR, they were talking to us through the headset and asking us questions which we did not answer. It's a very fun way of doing research. Okay, let's see if I can get to the last slides here. Oh, it's so slow. Okay, so next steps, we believe we will need an ethics variation to do AR participation beyond our ethics. So we're going to be looking into that and applying for that soon. Testing will do with a variety of users, including at B&R Enclosures. Some of the guys that work on the factory floor would be fantastic to see in this system. We'll also try and do an enabling of the user setup before we start. So placement of the cobot in different positions, different on the stand, on a rail, hopefully, and also maybe on the wall or a ceiling to see how it can change how people interact and where the conveyors go, and also other workflows and objects and objectives. And then we'll also look at other task metrics. Picks per minute was one which we've always been interested in looking at, and whether we can actually get better picks per minute. So picking up blocks and putting them down and see if we can beat the high scores, so to speak. And that's the end of the slides. I do apologize for the videos being so laggy. I will fix that, put them online. Any questions from anybody?
Hey Al, I was really interested in the I guess like the plugin or whatever you want to call it for the connection with Unreal Engine and ROS. Uh,
Yes,
I was just wondering, like, can I try it at some point? Like, what's the
absolutely. Yes. We're aiming to very difficultly put it on GitHub, and we'll be part of the ref GitHub when it does go up, James. Yeah, that's the aim. We do have a ref GitHub that we've set up for all the projects, and there's connection. It is very beta, James, but
That's
if
okay.
you
Yeah.
help in GitHub style and develop it by all means, because there aren't many. We've noticed that there are not many that exist out there which are robust enough. We've
No.
did this a lot. We've generally been very happy, and we've actually been quite amazed most of the time that it runs across an iPhone 5G, 4G signal, with not the lag that you saw in the video today. It does run quite smoothly, and very well, and it runs well on the headset as well. I've tested it up to about 45 minutes on the headset of just running. There does get to a point when the physics do slow down, because if you don't stop it, the blocks just keep appearing
Sure.
at the end of it.
That's awesome. That looks great.
Yeah, no problem. I'll get it your way. Thanks, James. Any other questions? I've got a message for Glenda. Thank you, Glenda. Thank you.
I have a question now.
Okay.
You talked about the theories as well, you know, that it's coming from a whole body of work that you're building on top of, which is really exciting to see. With the participants, I guess, can you explain a little bit more as to what you think, what you want to happen next? And is there going to be like maybe in the lab testing and then more in the wild at B&R, or what are your thoughts there? How many participants do you need? And
but the beauty of the system is that it's actually quite easy to test with. It's the barrier is not so much in being into the system, it's actually people using AR. And what we've found is that most people have tried an AR headset now. You hand them the controllers, you don't have to explain what to do. They work it out very quickly that you can grip the blocks, you can throw the blocks, and then you can use the trigger buttons to do things as well. So it's very difficult through the interface to break anything. We'd like to test here at the uni through the labs, and anybody who's also not tried VR before or AR before, that'd be fantastic. At B&R, in some of the early studies and surveys that we did, we found that quite a few people had already used AR or had like a PlayStation headset. So I don't expect there to be any difficulties there. I would like to kind of set up in one of the rooms at industry partners. I'd also like to take it to Striker and see if some of the Striker people can work with the system as well. As many participants as possible. More than 12.
right.
Magic 12, but more, as many as we can get. And we could get the system scaled to a point where I think we could get it running. On average, most people, I think, have enough of being in there after 5 minutes. And that's because we've slowed the robot down to a frustratingly slow speed, but we could speed that up and see what happens. Yeah, definitely. Thank you. Thanks for the question. Anybody else? I think that's it. Cool. Thank you. Thank you very much. Positive comments all around. Thank you. Thank you.
Thanks, Al. And
thank you.